written by these two authors, Mendel Rosenblum and John Ousterhout. So anyone recognize these names by any chance? Yes? Hint? For others?
Ousterhout's friend or one of them?
Yeah, he was, yes, he did a lot of work, but he's mostly famous work in this, but he also created this language called DCLTK, so it's kind of the scripting language. Yeah. Anyone heard of Rosenblum? So he's the. Oops. Something wrong. It's not advancing. Sorry about that. It's advancing on my screen, but not. Sorry about that. It's a Murphy's law, right? I mean, it can go wrong, it will go wrong, right? And Mendel is actually the founder of VMware. And what is interesting is that later he also wrote a paper about VMware, like where it all started, like the virtualization. It has a similar flavor like this paper where the technology really stood the test of time. Like later we'll talk about how this thing is basically used in every one of your laptop today. Okay, every SSD you buy, there's a lot structured file system in the firmware, but not so much their vision. Basically, all their motivation, their imagination of how people can benefit from this is all gone. Okay, the technology found its way in completely different problem. The same thing later on, the paper he wrote about virtualization. Right? He imagined it for one use. But really what got virtualization caught up is a different use. It's pretty interesting. Okay, so but really since I've been looking at the past events of papers we love, like browsing the topics. So I see there's a lot of very interesting papers, like talking about like audio searching algorithm and JVMs, JIT compilers, but there's no papers about operating system. Since I do research in operating systems, so basically I'll use this opportunity like give you some history, what I found is interesting, and the historical aspect of operating systems and in particular file systems. All right.
Dave, could you just point the mic more at your mouth?
Okay.
Thanks.
All right.
Yeah.
Cool. Thanks. And by the way, if you have any questions, just interrupt me. If I just go along, I only have 26 slides, so I'll probably finish in 20 minutes. All right. If you have questions, just interrupt me. Okay, a little bit introduction of myself. My name is Ding, and I work in UFT. I both teach and do research. I do research in operating systems and any basic system software. In particular, my research interests about reliability and performance. So basically, try to automatically recover from a failure or detect a bug. Okay. So in other words, for example, if you see your computer crashes, like for most people, it's like your oh shit moment, right? But for me, it's like my hell yeah moment because I still we still have work to do. So I got my PhD from University of Illinois in 2012, and then I moved to Canada and started working in UFT. So according to my wife, this PhD stands for permanent head damage, because I'm too geeky for her. All right. When I was a graduate student, actually, I worked in 2 startups. Both are founded by our research group. One of them did pretty well. It's called Pattern Insight, and later was acquired by VMware in 2012, the year I left. And I also worked in Microsoft Research. Our research has been used by quite a few industries, actually. Also, some of them through open source, and some of them through kind of software licensing, right? Like Hadoop, Google, Huawei, and Microsoft, NetApp, and that's about it for the big companies. And we also contributed hundreds of patches to open source project, Linux kernel, Hadoop, Cassandra, etc. Right? Okay, but I'm not going to talk about any of these today. Right? So now let's talk about this the topic of this paper, right? File system. Now the file system is really falling into this domain of storage industry. Okay, so and this industry is actually pretty interesting. Basically, the evolution of data storage hardware and software. If you have read this book, Innovator's Dilemma, how many of you have read this book? Yeah. So then this concept will be very familiar to you guys. Basically, this whole storage industry has been a running example in this book. And by the way, this is really the book that coined this term, introduced this term, a concept called disruptive technology. Basically, it's used today, overused. Every technology is called themselves disruptive. But really, according to them, what is disruptive technology is that at the very beginning, when this technology first emerged, it's unattractive. All right, it's going to be expensive. It's going to be slow. No one wants to buy that technology today when it first emerged. Okay, and that is also why it's so disruptive. Because if you look at its growth potential, I say 10 years down the road, how it will grow? It will grow like this in terms of performance or the reduction of cost on every aspect. It can really beat all the state-of-the-art mature technologies. And the storage industry is one of this industry. Then basically every new hard drive, and today SSD, when it first came out, for example, when the first 5 inches hard drive came out, no one wanted to use that. Okay, people laugh about that. People say, okay, it's too slow, too expensive, it's too small, no one is going to buy it. Okay? But then they fail to see the potential. So every new hard drive that comes out, almost you can see a new bunch of company that start to grow, and the old company just die. Right? For example, you guys know Seagate today, right? Western Digital, right? But have you guys heard of this company called Sugar? So Sugar was the Seagate together with Western Digital, together with like the Intel SSD, before this 5 inches hard drive went out. Okay, but they failed to see the potential and they just lose out. Okay, you just don't hear about them anymore. Okay, so again, if you read this book, they will talk in detail about this kind of a storage industry. And this is just a picture, right? This is all the hard drives that starting from the 60s or 70s. So this is the, I believe, 8 inches hard drive, okay? And this is the 525. This is 3.5, 2.5. I believe this is 1 inch, this is 1 inch, right? So basically, you can see it's getting smaller and smaller, and the older one just gets replaced, okay? So, and this is another curve, basically, it's more like that disruptive technology, right? So at the very beginning, when this 40 inches disk drive, you see it's basically back in the 80s, right, or before 80s, that's the state of art. And then when, let's say, 3.5 inches hard drive first came out, you can see this, the capacity is way smaller than these guys. And if you look at cost, it's way more expensive than these guys. Performance, speed is way slower than these guys. So that is why all the dominant player, the big companies at that time, they don't see the use. They can't see a potential. Right? They are too busy to make money out of their existing product. But for those startups who see the potential of these, to capitalize in these, then essentially you grow. Okay. So far, questions? All right. Then why do we need to talk about storage industry if we want to talk about the paper, right? The file system paper. Well, the reason is that for any file system, they are closely designed according to the hardware characteristic. Okay, so it's for us to explain why it's so cool, why that long structured file system, how it works, what's the benefit, together with what's the limitation. We have to understand how the hard drive works. Okay, so I'm first going to just show a video that explains this better than I do. All right.
An electric motor spins the hard drive's disk at exactly 7,200 revolutions per minute. The circuit board keeps the speed constant. And here's the crucial part. the actuator arms that hold the read-write heads. The ends of the arms are split, and right in the middle ride the disk platters. But the heads never actually touch the disks. The space between the head and the surface of the disk is 5,000 times thinner than a human hair. The heads float on a cushion of air created by the spinning disks. An absolutely essential cushion that prevents the head from crashing on the disk. And what a crash it would be. Talking about a crash is not only a metaphor. At these tiny scales, the weight of the heads really compares to the weight of a 747 airplane. A 747 airplane packed with 100,000 passengers, flying at 60 miles per hour, 1/100th of an inch from the ground. Ouch. There's no friction to slow things down, so the arms can move the heads to write or access data up to 60 times per second. The engine that drives the arms is invisible because it's an electromagnetic system driven by two forces of nature, electricity and magnetism, which makes the arms move back and forth across the disk at lightning speed. That's it for the components. Now here comes the data. The data is stored inside tiny concentric tracks on the disk's surface. During manufacture, up to 200,000 of these tracks are created on the disk. Each track is divided into sectors. A map of the tracks and sectors in the printed circuit board tells the heads exactly where to read or write information. The surface of the disk is smooth and shiny, but look closer. It's way more complicated. A magnetic film on the surface memorizes all the information. The heads magnetize microscopic sections of the film and store the data in a sequence of ones or zeros. Each one or zero is called a bit. The value of each bit is determined by the orientation of its magnetic field, plus or minus. And it doesn't take long for the bits to add up. One high-quality photo can take up 29 million bits spread across 12 different sectors of the disk. This sounds incredibly massive, but in reality, a stupefying quantity of bits can fit in an extremely small space. Each square centimeter of the disk's surface holds 31 billion bits. Now that's space saving. A hard disk stores and recovers a phenomenal amount of information at speeds that defy comprehension. Using the power of magnetism, the shiny surface of a hard disk can store the contents of several sets of encyclopedias, or hundreds of thousands of images. Easy. The hard disk really is an amazing, shrinking machine, squeezing mountains of data into little bites with a single keystroke. This masterpiece of engineering has really stretched the boundaries of physics, bit by bit. Coming up!
So although they claim it's so amazing, like so fast, but really later, as you guys already know, it's compared to the speed of CPU, compared to the speed of RAM, it's way too slow. Okay. But okay, let's take a closer look. All right. So this is basically how, if you open up a hard drive, this is how it looks like, right? You have multiple platters, and they are all mounted and kind of aligned together. And for each platter, both sides can record data. You have this called arm or head. They're perfectly aligned, always move in synchronization, right? And so they can read data from both sides. Okay. There's a lot of concept, but really one important one is called this track, and also another one is the cylinder. So what is the track? Basically, as explained in that video, the way you store data is track by track, right? There's a lot of small tracks, and each track is further divided by each block. It's called sector. Usually, you store 4 kilobytes of data. Okay, that's the unit of storage that disk kind of read or write. Okay, and then this is a track. If you take all the tracks on all these platters, that with the same diameter, right, or radius, that is called cylinders, right? A cylinder is all the data, all the tracks on all these platters, okay, with the same radius, right? Any questions so far? Okay, so that's how this look like. But why does it matter? Why do we need to understand it? understand it, it matters a lot in terms of performance. How do you store data so you can get the max performance from this thing, right, hard drive? By the way, if you have this question in your mind, okay, why the hell do we talk about hard drive, right? Today's the SSD age. How many of you have that question in mind? Okay, so later we will see. Okay, later we will do the same introduction, breaking down SSD to look at its hardware characteristic. But the reason we need to understand this is that log structure file system and all the other file systems that before it, they are heavily optimized for this physical characteristics. The same way that why log structured file system work really well in SSD. It's basically really matches the hardware characteristic. Okay, so we operating system researcher, we always like to joke that we are always pushed by hardware guys. We are always pushed by Intel. Right? Okay, so now this performance really, there's one thing to remember is that random access is slow. Or in other words, sequential access is fast. So what does that mean? It means, let's say this is your disk, right? And you store data in all these sectors, right? Now, in order for you to access that data, right, doesn't matter whether you are going to read or write, here's what's going to happen in the disk level, right? Let's assume your data block is stored somewhere here, okay, on your disk. Now, once your OS to say, I want to read it, once the disk gets this command, what happens first, it will spin the arm, right? I need to spin my arm to this radius so that the data can fall, can kind of spin to here. If my disk arm is here, I cannot read that track, right? I first need to spin my arm. And that spin of the disk arm is called seek, right? So if you have seen like how a CD drive works, it's the same, right? Okay. Now, in that video, they claim it's really fast, right? 4 milliseconds, okay? 4 milliseconds is fast. As a human, you don't know how fast it is because you cannot comprehend it, you cannot perceive it. But what's the CPU speed? Nanosecond, right? That's 1,000,000 times slower than the CPU, okay? To put that into perspective, let's say take the speed of the fastest rocket today versus the speed of a snail. That is not even 1,000,000 times, okay? That's the speed discrepancy we are talking about, all right? And this is just the seek, right? Just for you to move your arm, right? Now, but it's not done. You first move your arm there, and then you need to wait. You need to wait the disk to spin so that this data block finally spins underneath your arm, okay? Now you can read it. So before you can even start reading or writing that data block, you're spending milliseconds, over 5 milliseconds of wait, okay? So that is why people always say hard drive is slow. And it's not going to get better. Why? Because it's limited by this mechanical part, right? Your CPU, all these are limited by the speed of light, but this is not. This is limited by how fast the mechanical part can move, all right? It's going to be bounded, it can't improve, okay? Then let's say now, if you have the problem that you want to store 3 data blocks, 3 blocks, right? 12 kilobytes. Now you face a choice. Where do you store them? How do you store them on the disk, right? You could store them like this, one next to each other in the same track, okay? Like this, all right, with the same radius, okay? Or you could store them randomly apart from each other, okay? And let's assume if these 3 data blocks are the 3 consecutive blocks of a file, what should be the design? Sequential, right? You want to store them together. Why? Let's take a look, right? So if you're smart enough to store them together, one after each other, and you know that most likely your workload will read these blocks together, then this is what happens. The first time you read a block, you need to suffer the seek, right? You need to suffer the rotational delay, but that's it, okay? In order to read these 3 blocks, you only need to suffer 1 seek and 1 rotational delay, right? And then once you can start with read, first block, the next block is immediately after this one, and then the next block, right? So this is why, this is called sequential access. They're next to each other on the same track. So you do not need to suffer seeks in the middle, okay? But if you somehow scatter them around, apart from each other, you want to read them one by one. Then the first time you read this block, you need to seek, and then wait for the rotational delay. The next time you are going to read this block, you need to seek again, and then wait for the rotational delay. And then the third block, you need to wait for the seek and the rotational delay again. And again, your disk is slow because it's the seek and the rotational delay is slow. The data reading is much faster. Okay? So this is what we mean by random access is slow. We want sequential access. Okay? You want to put frequently accessed data together, close to each other, in the same track, in the same cylinder. Okay? So far, any questions? Yes.
With the mechanism, all the arms are always in the same position. Is that right?
Yeah.
Okay.
Yeah. So they're always synchronized. Okay. So that is why actually it's still better that if, for example, if you cannot find available space on the same track, you can find some other tracks but in the same cylinder, some other patterns. Okay, that's still going to be faster because you do not need to seek anymore, right? Okay. All right. So that's this. Okay. So that's once we understand how this works, we can start to talk about file system. So first, what is file system? File system is this piece of software that basically organizes your files and directories. Okay, you take it for granted today. Okay, you open a file, right? Doesn't matter whether you use command line or use this graphic user interface. You have files and directories. The file system is this piece of software that organize them and store them onto the disk and find them when you want to read or write those. Okay, so basically the input to file system is the disk. The output, it provides this interface, give you the concept of files. Okay, the concept file is really created by file system. And today, file system, this concept or directory is provided by the operating system. So file system is this piece. Today is always together with the operating system. All right. Then, really, what file system need to solve? The problem need to solve. There are two important problems. One is that what is the logical organization? Basically, how do I write my data structure so I can piece together the files and directories? So when you say /var/log/syslog, I can find it. Okay, I can start from this slash with the root directory, all the way find the file that you want. Okay, so that's the logical organization. Okay, and the second problem is the physical layout. Okay, you can implement your data structure, you can write your program, organize all the pointers so you can find all the files, but someone need to allocate them into the disks. Okay, why does it matter? Because as we just explained, where do you allocate those blocks on the physical disk has a huge impact for the performance. Okay, so now let's look at these problems one by one. All right. So first is the logical organization. Okay, and in fact, the logical organization of all the file systems used today, including that log structure file system, including your MacBook, including Linux, including Windows, and basically Android, right? It's any operating system is pretty much the same. So that's called the Inode. Okay, it's really kind of that was introduced by this paper, the Unix time sharing system. Okay, this is a paper from 1970 something. Okay, 74 I remember, right? So, and if you read this paper, it's like reading an operating system textbook. Okay. All the technologies they say here still the test of time. It's still the state-of-art operating system technology. Except that, for example, something like this, right? I mean, Unix can run on hardware costing as little as 40,000. Right? That is basically out of date. But really, all the technologies, right? It was still a small computer, yes. So, and these guys, Dennis Ritchie and Ken Thompson, they basically went touring our world, partly because of this work. Okay, so actually, if you look at the motivation of Unix, so does anyone know that why did these two guys decide to write Unix, write a new operating system? that's part of the story. But really what happens was that at that time, these two guys, they worked in Bell Lab, okay? Before Bell Lab, before Unix, there was this Multics with gigantic operating system that's run on a so-called kind of, at that time it's called a very powerful server, but really not even more powerful than your iPhone 5. But this was designed to service all the computational need for the entire Massachusetts, okay? And it was a gigantic project. But in the end, commercially, it failed. It couldn't make money. So a lot of companies just pulled out, including Bell Lab, okay? Then what happened was that, at that time, Ken Thompson, he had a game called Space Trial. Right? He wrote a game that he can play every day, but that only run on Multics. But once Bell Lab pulled out of the project, he can no longer run his game, right? So now, in order for him to run the game, he decided to write an operating system. That was the start of Unix. And in fact, this Unix, the name was named by Brian Kernighan, was actually a fellow Canadian, U of T alumni. At that time, also working in Bell Lab. The reason it's called Unix is because it's so simple. It can't do anything but run that game. So they call it basically this kind of unicorn. It's like a Unix, right? And the first version of Unix was written in assembly code, and it served the purpose. They can run game. And then Dennis Ritchie joined the project to say, okay, that is cool, but then he wanted to improve it, but find, okay, it's very hard to program in assembly. So Dennis Ritchie invented the program language C, okay, so that they can rewrite Unix in a higher level language, okay? So that's basically what these guys did, all because they wanted to play a game. But actually, it's interesting that if you look at all these fundamental breakthrough of computer, it's because those people at the beginning, they want to play games, okay? Operating system is one, right? Internet, why do you think when internet started? Because they wanted to play online game, right? How mouse, graphic user interface, how they got invented? Again, because people wanted to play game, all right? So they are really driven by their interest. All right, so then what is cool about Unix is that at that time, they are first proposed this new way of organizing file and directories or kind of logical, okay? And that is called Inode. It's basically proposed by this paper. And this is how it works, okay? Again, the problem is that, okay, you have all these files and all these directories. How do you find them? Essentially, you need some pointers to point them, to link them together, right? What is the data structure, okay? And Unix, basically, Dennis Ritchie and Ken Thompson, they basically say, okay, this is the data structure, all right? The key data structure is something called Inode, okay? I stands for index, okay? So like a pointer, all right? So on any file system today, for every file, any file or any directory, there is additional disk block associated with it. It's called Inode, okay? One for each file. There's no exception, but there's only one for each file, okay? What gets stored in the Inode? Basically a bunch of pointers. Let's say if your file has one block, okay, if your file is small enough, less than 4 kilobytes, you only need one disk block, right? There'll be one inode together with it, and this inode will have an entry stored in the disk address. Essentially, it's like a pointer telling you, okay, where is the first block of this file, okay? And if your file is larger, it has 2 blocks, so the next entry is the pointer to the second block, okay? So together, if your file the size is less than 12 blocks, then there are 12 entries. They call it direct pointer, okay? You go to that location in your inode, read that address, that's a disk address, tell you where that block is, all right? But clearly, you know, your file could be larger than 12 blocks, that's what, 48K, right? So the way they solve it is that there are 3 more entries in each inode. They are called single indirect, double indirect, triple indirect, okay? So this is still a pointer, a disk address, but the destination of this disk address is not a file content, but it's a block full of pointers, okay? Now within this block, there are a lot of other pointers, and each pointer will further point to a data content block, okay? And if this is still not enough, you can use this entry, right? basically then the 14th entry here in this inode, because the index starts from 0, this is called double indirect. It's a disk address taking you to another disk block. On this block, it's going to be interpreted as a bunch of pointers. Each pointer is another disk block full of pointers, and these pointers will point to the actual file content. And the triple indirect basically is like star, 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 right? You see basically 3 levels of pointers, all right? And this is how you find the file. Or basically for each byte in your file, you starting from the inode, eventually can find it, okay? If you want to read byte 0, you just read the first pointer and take you to the first block, okay? If you want to read some bytes from the second block, read the second pointer and take you there, etc., etc. Okay? So as you can also see that the larger your file is, you need to spend more time just to locate that block, right? Okay, so far any questions? Yes?
How do you arrange those, how do you order those for physical sequential blocks of the actual data?
Exactly, so that's something we are going to discuss. That's a problem not solved by Unix, but the question is really how do we store this onto the physical device, which have different performance implications, right? Okay, so and there, the inode also stores some metadata, such as, for example, the timestamp, when's the last time you had access, the owner, the permissions. If you're curious, on any Unix machine like Linux or Mac, if you just, in the command line, you just type stat, right, STAT, a file name, it will basically show you a bunch of file statistics. All this information essentially are stored in the metadata of the inode. So in order for you to execute that stat, you do not really need to look at the file content, but you only need to read the inode of the file. Okay. All right. So let's look at an example. Let's put it in action. Okay. Let's say if you want to read this file, right? /var/log/syslog. Okay. Now, how does the computer or the operating system find this file for you? Okay. And this is what happens. Okay. Now each yellow block is an inode, and each brown one is a data block, okay? Now the first important concept that's introduced by Unix, used by all the computers today, is that from a file system perspective, there's a little difference between a directory and a data file, okay? In the sense that it doesn't matter whether it's a directory or a data file, there is always inode, okay? And the inode structure is the same, okay? But the difference is that the directory, the data content of the directory has a special format, okay? What is the format? Essentially, it's like a table with only 2 columns, or a key value pair you can think of, all right? So basically, the key is the file name or the subdirectory name, okay? And the value is the inode number, where you can find the inode of that file, okay? Now let's start from the very beginning, all right? So in order to find any files, the file system or the operating system starting with just one root. That's basically the root directory, right? /. Right? This root is a directory. It is an inode, okay? On any of the Linux machine today, this inode, every inode has a number, okay? It's an ID. That ID is 2, okay? ID 2 is for the root directory, okay? You first find where the inode is, and then you read the first pointer. It will take you to the content of this root directory. What the content looks like this. Remember 2-column table, key value pair, right? Basically, these are all the files or subdirectories stored under this root directory, okay? And then the value is the inode number of that file or directory, yes?
If going for inode, is there also basically another index that says this inode is at this block on the disk?
Yes, yes. There is a good question. There is, this number, this ID is a logical number. It's not a disk block, okay? There's a way to translate this logical number to the actual disk block that stores this inode, okay? And that is up to for the implementation. Usually, most of the system today, there is like a hash code, okay? They go through some algorithm. So basically, input a inode number, that algorithm will calculate what is the disk block number. But that's different for the log structure file system. Later we'll see how they map this ID, inode ID, to the disk address of this inode. Okay, all right. Okay, so now after you find this, okay, this inode will take you to the content of this directory. You're going to find, okay, what is the subdirectory? The next level directory is what? Var, right? You're going to find /var. You're looking for this entry, right? You have an entry that named the var, and then the value is the inode of this var, right? And that will take you to where this inode of this /var is located. This /var is another directory, right? And then you go to this directory. The data content is the same, right? Basically, the same format, a key value, okay? And then there will be an entry called the log, okay? If it does not find the entry, it means you can find this file, right? It's not in this directory, okay? Because you have this entry, you are going to treat the value 5193, that's the inode number, take you to the inode of this /var/log, okay? And the same thing, this is another directory. So you further look at this, the key value pair, find this file name called syslog. And this is the inode number, 6264. And then this will take you to the inode, the index of this syslog. And this is the data file, right? You're going to really read it. But still, the way you'll find all the data block is the same. You look at the first block pointer, the second block pointer, and that will take you to the first data block of this /var/log/syslog, and the second block of this file. Okay. So in other words, every time you're going to read a file /something, step by step, this is how the file system eventually find that file. And the good thing is every file is going to be located because every file will start with the same root, the slash, right? Essentially, file system is like a big tree, right? Okay, so far any questions? Okay, but you can also imagine this can be pretty slow if you have to do all these directory walks, right? So all these things are, the inode and the directory content is heavily cached into the memory by the operating system. Okay, the first time you may be slow, but next time you access another file in this /var/log directory, all these data are cached in your memory. Okay, all right. Any questions so far? Okay. Now that's the logical data structure, and that really stood the test of time. None of the later file system, including the log structure file system, changed that. Okay. Today it doesn't matter what log file system you are using. It could be a log structure file system, but internally, this logical indexing will still use this inode. Okay. The picture I showed before. Right. But the difference is how do we store the data onto the physical device? Okay. You have all these blocks. Some blocks need to store the inode. Some blocks need to store the data content. Where do I store them? On disk. Again, why it's an important question is that if you store too frequently access the block far apart, so you are going to suffer the seek time. It's going to be slow, okay? So that is the problem from now on we are going to talk about, right? And that's actually hit one of the limitations of Unix. When Unix first came out, it was a slow operating system. The reason is because they did not do a good job in terms of physical layout. In fact, they didn't put much consideration in terms of where do I store this data onto the hard drive. Okay, so for example, intuitively you would think the inode of a file and the block content of that file, they are going to be frequently accessed together, right? So you want, because they are frequently accessed together, you want them to be close to each other on the same track, for example, not far apart. But Unix doesn't even do that. Okay, in fact, they separate the inode and the data content far apart. So every time, for example, in this picture, you go from here to here. The way you store it on the disk is that you have to seek. You go from here to here, you have to seek. From here to here, you have to seek. You're talking about multiple milliseconds. Okay, yes?
Sorry, is this with like modern exe file systems, or is this with virtual file systems?
That was the original file system. That was gone. Okay, you're not using that. Okay, you're not using that. Right. Okay, so it was really cool. Okay, and then it came to it's good you mentioned ext. This essentially is the paper that really basically all the technology used ext2, ext3, is basically described in this paper, right? So it's called a fast file system for Unix. It was published, I think, in 1984, okay? Exactly to address the problem of poor performance of Unix file system. Do you guys recognize any of the authors here? Bill Joy, yes, that's the Bill Joy. Okay, that's the founder of Sun Microsystem. Okay, again, it's an interesting story. So Unix was created by Bell Lab, right? And then Bell Lab actually they started to commercialize this. Okay, they want to charge heavily of the license of Unix. And to a point where, but also after Unix first introduced, because for a period of time, due to some antitrust lawsuit, AT&T was basically ordered that they have to give up the source code of Unix for free. So that is why actually it's gained a lot of traction in industry and academia, because people are familiar with all this concept, and it's really a kind of very cool working technology. So basically, then not only that people are using that, it's basically standardized, right? If you look at the POSIX standard today, right? Like all the system calls or signals, they're essentially Unix. They're defined by Dennis Ritchie and Ken Thompson in Unix, right? But later, actually, AT&T kind of they got greedy. They want to charge a heavy license, like $20,000 per license per installations for Unix, okay? And then people say, okay, basically that can be it, right? They are looking for alternatives. At that time, basically DARPA, this defense government in the US, they decided we need some cheaper operating systems that are Unix compatible. Basically, the application I wrote that was working on Unix can still work on this operating system, but I don't have to pay a lot, okay? And they basically gave out this millions of dollars of grant to University of California in Berkeley, okay? So that they can write this free operating system. That's why it's called FreeBSD, okay? Berkeley Systems distributed something, right? So is there a comment or something?
Berkeley standards.
Yes, you're right. And at that time, Bill Joy was an undergrad. Okay, he was an undergrad. When he was an undergrad, he was already a co-founder of Sun Microsystem. All right, and all his other co-founders move out of the campus. They started to build the machine and software. But they heard of this thing. They heard about this movement that DARPA is going to give a big money to investigate the latest OS technology. Okay, and they told Bill Joy, okay, you stay in school, right? You participate in this project. Okay, you learn basically from all these academics how to build an operating system, and then after you learn all these components. Okay, that is why Bill Joy actually he was one of the first couple people in this BSD project. Okay, so he was co-author of a lot of the early BSD papers, and he really built BSD, and then afterwards he then moved to some microsystem, and they built this open Solaris, right? But at that time, all the key technical challenges is already solved. He knows exactly how to solve them, right? Okay, so back to this, right? Basically, this FreeBSD fast file system is that project, the FreeBSD project, okay? And then this paper is just to try to solve the problem of Unix is slow on this, okay? But they are not trying to change anything about the logical organization, okay? Still the inode, okay? Still that's using inode, and gradually you can find all the files. But the only challenge or the technology is around how do they store those data blocks smarter on the disk, okay? So the high-level principle is very simple, okay? It's basically minimize the number of seeks, okay? It's going to be heavily guided by the actual workload. They basically want to see, okay, under the common workload, what are the frequently accessed blocks together? And if they know these are frequently accessed together, they try to put them into the same track or the same cylinder, so there's no seek. All right. So what are the frequently accessed blocks together? Well, for example, the inode of a file and this inode is together, right? Don't separate them. Put them on the same track or the same cylinder, hopefully next to each other. That's the idea, right? If you have multiple files in the same directory, right? You want to put at least the inode of these files together, right? Why it makes sense? because typically you type ls on a directory, right? You want to look at, okay, what are the things under this directory, right? Those information, like those file metadata information, displayed by ls-l, okay? They're stored in inode, right? At ls-l, a directory, you are going to access every inode of the files under that directory, right? So why you want to put the inodes of the files in the same directory together. What do we mean by together? Basically, on the same track. We're on the same cylinder. There's no seek, right? And what else? Okay, so blocks of the same file are placed together, right? Because they are likely going to be frequently accessed together. Okay? Yes?
So you said this paper came out in what, 94?
84.
Oh, 84.
Yeah.
So before then, like if you had a directory with 1,000 files in it, then and each one needs a separate seek,
Exactly.
then it's like 5 seconds to list.
Exactly.
Yeah. Yeah. Okay.
Yes. But at that time, people will argue, if you talk with Ken Thompson, he's in Google, right? Talk to him a couple times. He will say, look, these are the things for your grandma. These are not the things for programmers who knows how to write your program smart. Right? Multiple people, for example, they made all these remarks, like, for example, every time when the number of bits, you want to go expand, your computer want to go expand from 16 bits to 32 bits, multiple people will jump out and say, why the hell do we need that, right? Why the hell do we want to write a program that needs 4 gigabytes of memory, right? People are crazy, right? Bill Gates once said that, right, from 16 bits to 32 bits. But, I mean, I'm sure they probably found this.
They would just say don't have 1,000 files.
Exactly. Right. Okay. Okay. So all these technologies right now looks intuitive, and they are indeed also work, right? Basically, all the today's file system on your hard drive, they use these technologies, design principles, EXE2, EXE3, all these tech, and like file system used by macOS, right? Basically, they try to optimize for the physical layout. Okay. So, any questions? All right. And after that paper was published, again, that paper was really kind of stood the test of time, right? People thought, okay, stop, okay. As long as we are still using hard drive, problem is solved, right? Don't have any more problem. Just use fast file system. Every new operating system at that point came out, implement this fast file system. Right? Until this paper, right? And in '91, these guys, Rosenblum and Ousterhout, they kind of introduced a new design, right? And they actually, it's called log structure file system. Later we'll explain, basically the reason it's called log structure is because they treat the physical disk really like a log. It's append only. Every time you write to the end, just like you write to a log, right? For a log, you never do in-place update, right? You always append to the end. That's how they write data. They do not do in-place update. They always write to the end. If you want to change a byte in your file, your old byte is somewhere on your disk. They allocate a new block containing that byte. Okay, that's the idea. That's why it's called log structure file system. But really, why it's kind of named log structure file system is because actually it's related with the actual log we are using. So at that time, actually, we started this project by trying to solve the problem. Is that at that time, later, after the Berkeley fast file system, a lot of file system research and technology, they try to address the reliability or durability of data or consistency. Basically, the problem is that, for example, let's say in this picture, right? For example, if you want to create a new file, right? If you want to create a new file under this directory, okay? What do you need to do? You need to add a new entry here, right? Okay, file name, and that new inode. Allocate a new inode for that file, right? And allocate a new disk block, right? These are the 3 steps you need to create a file, right? But what if it crashes in the middle, right? Because there are 3 disk accesses, right? You need to write the disk 3 times. No one's guaranteed that you don't crash in the middle, right? If your computer crashes, you could result in an inconsistent state. Okay? For example, you already wrote this entry, right? You wrote this entry, but you haven't allocated this inode or not yet, right? Then this pointer will point essentially to a random disk storage that is not formatted yet. Then you lose power. The next time you restart, your file system in an inconsistent state, right? That is why actually earlier years, sometimes when your computer crashes, when you reboot, you will have this blue screen to say, okay, I'm doing consistency check, right? I'm going to check my file system consistency. It's going to take you a while. You have to do this kind of progress bar going really slow, right? What it's doing is fixing all these pointers, right? Okay. The way they solve it, and it can get much trickier than the scenario I just explained, right? The way they solve it is very simple. It's use a technology called journaling, okay, which exists in all your file system today. The idea is that before you do any write, actual write, to change your file system, all these pointers, you have a journal. A journal essentially is like a log, okay? It's only for crash recovery, okay? It's only for that purpose. You log that operation in the journal, and then you do actually all these disk write, okay, to create all these pointers. Then the good property you have is now is that if you crash in the middle, the recovery just they look at the journal, okay? The journal of operations to see, okay, now you have an outstanding operation. I check this operation, is it my disk image, is it consistent or not? Okay, if it's consistent, fine. But if the disk image is not consistent, for example, I allocated an entry, I added an entry here, but this block does not correspond to that. I know exactly what happened from my journal, my log, because I was trying to create this file, and I can go back or redo it, right? Finish this operation, okay? Now the good thing is that as long as you log something to, so because you only do things after you log it from your journal, so your journal is trustworthy, right? Basically everything you hold is in the ground truth is in that journal, okay? But this solves the reliability problem I just mentioned, but it introduces a performance overhead because the journal is always also stored on the hard drive, right? So then Ousterhout and Rosenblum, they are trying to solve the problem that, the problem is that every time now you do any disk write, you are also going to write to that journal. You are paying the performance latency for another write, and that should happen before your actual write, right? Yes.
What if you crash when writing in the journal?
Oh, you crash writing the journal? Good question. If you crash writing the journal, your journal is not consistent, right? Your journal will be like you have an entry half full, right? But that's perfectly okay because you haven't started your actual operation on your disk yet. Your disk is not inconsistent. Your disk is consistent. Okay. So, a good question. Okay. Then you are basically having another write to the journal, right? How do they solve that? That's a problem you try to solve. Okay. And their idea is that okay, if I really treat my disk as a big log, I do not do in-place update. I always append to the end. Then I might solve this problem. I do not need a journal anymore. Okay? That was their whole idea, whole motivation, why they try to come up with this kind of log structure file system. Okay? Later they package a lot of nice motivation to say why it's useful, but that's what their real motivation. All right. Okay, so yes. So let's make very clear. Okay, what is new here is the new physical layout, but not logical organization. They still use Inode, still use basically that picture, that pointer picture proposed by Unix, okay? So, but they really change the physical layout, okay? So, and the motivation really listed in the paper is that, number one, is I/O traffic is going to be dominated by the write. So disk is slow, so you care about the I/O time, but it's dominated by the write. Why? Because they say, okay, your read is likely to be cached by the memory anyway. Why they say the technology trend is that memory is always growing, right? The capacity of memory is growing, okay? So you have larger and larger memory. You can afford to cache a lot more things, so you can cache all the read, okay? But you can't cache the write. Why? Because you care about durability. You want your data to be on the disk, right? So That was their motivation. So basically they say, okay, I don't care about read. Read performance is going to be served from the memory anyway. I just care about write. Okay? So far, any questions? Okay. If you find this a bunch of just bunch of bullshit, it is. Right? In the end, those motivations not why log structure file system got released. And secondly, is basically it's what we have discussed, right? Sequential access is way faster if you talk about the time spent per byte compared to random access, right? If you are going to write to the disk, you want to write them sequentially. You want to allocate blocks. Let's say you want to write 1 megabytes, right? 1 megabytes is what 250 blocks, right? You want to put them one after each other, just one write, one after another, so you have just one seek instead of over 200 seeks. Yes.
So if you're write dominated, maybe you want to write wherever you can access right now, rather than making it more sequential by seeking to where they would be in order for your reads.
Good question. Good question. Yes, yes, sure. You want to, that is an optimization that it's going to buy you something, right? It's going to get you some gain. And they actually later when we talk about, they kind of have that property, but really they will talk about is that even if you forget about the first seek, right? If let's assume you are going to suffer a seek in the first place, but later really if you want to have, let's say again, in the end you want to write 1 megabytes, right? You do not want to separate them into a bunch of random writes. You want to combine them together. Right? Okay. Good question, all right? So far, good, right? That's their motivation, okay. Okay, then what is their idea, okay? They treat the entire hard drive as a log. What do you mean by treat the entire hard drive as a log? A hard drive from a programmer or from an operating system programmer perspective, it's just a big flat address space, right? One-dimensional from 0, 0 to whatever your capacity is. You have all these blocks you can use, right? I treat it as a log, okay? I always write to the end. I always append. I never do in-place update. Even if you want to modify 1 byte somewhere in the middle, I do not touch that byte. I do not touch that block. I find another block at the end of the file, which at the end of the file should be always free space. I find the block, I write that byte here, together with all these remaining 4,095 bytes. Okay, I copy them, just so I can update 1 byte. Yes.
Does it do any kind of compaction over time?
Good question. Yes, they have to. That's where the whole thing breaks down. Right? We'll see. Okay. All right. Where were we? Okay. So append only, right? Append only. No in-place update. Later we'll see how it exactly works. That's the idea. Okay. And then once they do this, another technique is that they are going to buffer. They are going to buffer a bunch of write, right? Let's say you are going to have write for 1 byte or another write for another byte. They are not going to immediately issue those byte. Okay. They are going to, okay, so in your program, you say, for example, fprintf, or write to the file, okay? This system call, this function call will return as long as that data hit the RAM, hits the memory, okay? They won't wait until it hits the disk. They are going to buffer all the write. Once they buffer enough write, they are going to write it all together. They are going to convert a bunch of very small write into one large sequential write. It's going to be a large write, it's going to be a sequential write to the end of your log. Yes.
So if they're updating a byte or they create a new block then, right? But they do that in the inode as well, so they create new inode as well.
We'll see. Okay, good question. So there are some technical side of it there, right? But what about read? Well, again, who cares? They don't care, right? They don't care about read. Okay, read is cache. Okay, they don't care. They don't worry about it. Okay. Okay, so that is interesting. But let's see how it works. Okay. Now I'm using this example to show how it works. Okay. Let's assume we are going to create a file under this release dir1 or dir. So there's some consistency. Basically, the same directory dir/file1. I'm going to create this file. And I assume right now this directory already exists, but this file does not exist. All right, that's assumption. Let's see how it works. So this is your disk layout and your kind of conceptual logical organization look like before this operation. Okay. So you have inode for this directory. directory 1, okay? Let's assume this inode number is number 45, okay? It occupies a disk block, okay? And then in this inode, you will have a pointer, right? And this pointer, now I gave a concrete value. This value is a disk address, okay? It's a disk block address. Tells you that where you can find the content of this directory. Assuming now this directory has one file called file 0, okay? So now this is your actual physical disk layout. Now this physical disk has only 10 blocks, okay? They are basic address 0, 1, multiplied to the 9th block, all right? So now I'm saying, okay, block number 2, this block is a disk address. It's going to store this, right? And this is the directory entry that tells you, okay, right now I contain this file 0, and what is the inode number of this file 0, right? Okay. And then I also need a disk block to store the inode, right? Okay. So let's assume in this case we store it in block number 1, okay? Block address number 1. We have a map, okay? They have a data structure called inode map. What does it do? It basically map the inode number, the logical inode number, to the actual physical block that stores this inode. Okay? So this means inode number 45 is stored on disk address 1. Disk address 1 right now is my yellow inode, right? This inode pointing to the data of this directory, dir1, in disk block 1, disk block 2. Right? So far, question. Okay? This is basically same as the previous CR form.
Is the inode now actually containing physical addresses as opposed to logical addresses?
So all the inode number are logical. So you need additional mapping to map
So there should be 2 entries in that map, right?
in this map.
Yeah.
Now there's a key value, right? It's only an inode number and the disk address.
But what about inode number 2?
Oh, this is not inode number.
That's
That's
physical.
physical address.
It
That-
contains a physical address.
Exactly. In the inode, you directly store the physical address. Okay. In the inode, you only need a mapping to find the inode. Once you find the inode, you can directly use the content here, interpret it as a disk address to find the disk block. Clear? Right? Okay. Now you are going to create this file, right? Let's first see logically what you need to do. Right? Let's first see here. This is logically what you need to do. Okay. Forget a little bit about physically what you need to do. Logically, you are going to allocate a new inode, right, for this file. And let's assume this file has two disk blocks, right? More than 4 kilobytes, right? Let's say 6 kilobytes, for example, you need 2 blocks, right? You need to allocate 2 additional disk blocks somewhere, right, to store it, okay? And then you need to add a new entry here, right? You need to add a new entry in the directory of this dir1 to say file 1, because I now created this file named the file 1, and whatever this inode number. Again, this inode number is a logical number, 86, right? Okay? So far, so good. Okay, that's exactly the picture used by the fast file system, used by Unix. Okay, logically, that's why it's exactly the same. Now the question is, how do we physically store it? Before we talk about that, okay, let's think about, in this case, just to create this file, what data did we change? Clearly, we allocate a new inode, so that's change, right? We allocate 2 other blocks for the file content, that's change. We also modified this thing, right? The directory content, because we added a new entry, right? That's change, okay? But so far, under the old file system, you do not necessarily need to modify the inode of this direction, okay? You do not have to. Or if you're sharp enough, you know you still have to modify it. Why? Because there's a field called the last access time, right? You need to update that timestamp, but maybe you do not have to. Let's assume that you don't have the timestamp, so you do not necessarily need to modify this, okay? Okay. But now let's see, using their idea, how do they really store it onto the disk drive? Again, the principle is that no in-place update. We are only going to append to the end. Let's assume here is the end of the log, okay? So starting from block number 4, all the way to the end of your disk is free, okay? It's free for them to write. That's where they are going to start to write, okay? They are going to say, I'm going to write this file, because you have updated this block, I'm going to allocate a new block just to reflect this write. Okay? I'm going to allocate a new block to store it. And forget about the old block. It's garbage now. Okay? This is a new block. And all these 3 blocks are going to be allocated at the end, right? The benefit, again, sequential write. Next to each other, sequential write. Yes, question?
How do you mark that block as garbage?
Okay, good
Because
question.
whatever reference that can also be updated and changed.
Good question. Good question. Later we'll see. Okay, good question. Keep that in mind, all right? So far so good, right? But now, okay, remember the problem is we changed this block. What is this block again? This is the content of that dir1. We modify it. We are going to allocate a new block. The address of this dir1 content is changed. It's no longer block number 2. Now it's going to be block number 5. What does that mean? It means we need to update this pointer, right? Remember there's an inode for this dir1. We need to update this pointer. This pointer is no longer valid. If you do not update this pointer points to block number 2. Block number 2 is your old block, right? We don't do in-place update, we allocate new one. So as a consequence, you also need to modify the inode of this dir1. How do you modify this inode? You are going to change this pointer to number 5. Because 5 is a new block, now you allocate it for this direction. Right? So that is why we modify this, again, according to their principle, no in-place update. They are not going to touch this block. They are going to create a new block to store the inode of dir1 because you have changed that pointer. Okay. So what happens is that for this write, create a new file, essentially all these blocks are going to be modified. They are only going to allocate 5 new blocks, okay, like this, towards the end of your log, and each block content is going to look like this. Remember, we have an inode map, right? Inode map, what is inode map? Maps a logical inode number to the actual physical location of that inode, right? Now in this picture, we have two inodes. One inode for dir1, one inode for dir1/file1. Right? The inode for dir1, right, is basically 45. That's the inode number. The disk address changed, right? Previously, it was there, right? But now we have allocated a new inode, new block for this. I need to change it to 4, right? I updated my inode map, right? And then I allocate a new inode logical number 86, pointing to disk address number 6. Okay? Consistent. This picture is consistent. All right? So far, so good. Back to the question, right? How do you know? These now become garbage, right? All these things become garbage. How do I know they are garbage? Because exactly, nothing points to it. Your inode map, remember your inode map contains 1 entry for every inode in your system. What does that mean? It means, remember every file or every directory there's 1 inode, right? So there's 1 entry for every file or directory in your system. Okay? So as long as you have this inode map, you know where are the latest copy of each file. Okay? So any disk block that is not pointed by the inode map, and subsequently the pointer is pointed from that inode, is all garbage. Yes.
Don't you need to also look at the garbage inode to find out the disk addresses of the file contents that are also garbage?
True.
Okay.
True.
Okay.
That's right. But later they do some normalization to help you to, without looking at the reference, tell you where the garbage is. Yeah.
So I also had a question. Where is the inode map stored?
Good question. Where is the inode map stored? What do you guys think? Number one, it's going to be frequently accessed, so it has to be cached in the memory all the time. All right? But in addition, it has to be durable, right? If I crash, I can't lose my inode map, right? Because that's going to tell me where exactly is the latest copy. So it's both cached in the memory and stored on the disk. Where it's stored on the disk? Again, same principle. Every time you modify inode map, there will be a new inode map that is appended to the end.
Is the whole thing?
The whole thing. The whole thing, right? But that's relatively small, right? Because it's just a bunch of pointers. Still, you have a lot of files, but let's say if you have 1 million files, 8 bytes for a file. That's still a lot, but right, okay, relatively small. Okay. But basically, again, every time you modify inode map, dump it to disk. You do not overwrite the previous inode map. You write it to the end. Yes.
Can you have basically an inode read that is just directories? You basically fill out the whole disk space, but you don't have any useful files on it. Is it possible?
So to run out of disk space, you run out of the disk space. Is that the question?
Just to keep the inode,
Oh.
large inodes.
So just to store the inode map, is that what you're saying? Well, sure, they do have inode map, again, relatively small, right, relatively small. But they do have a problem, they can quickly run out of disk space, right? Because they never do in-place update. So whatever, anytime you write, essentially all these things are essentially garbage, right? They always append to the end, okay? Sure, you have good performance, but only if you have abundant disk space at the end, so you can always append to, right? Or it quickly become garbage, you need to garbage collect, right? So one of the key problems this log structure file system need to solve, you need to garbage collect. You need to get rid of this, you need to want to reuse those disk space, right? Yes?
Sir, why would you need garbage collect? Like maybe I missed something, but aren't you just kind of rolling around this? Like they circle once you're hit?
Good question, right? Good question. Okay, good question. Anyone want to answer that?
Well, it's not like you still have gaps between the files.
Exactly.
Oh no, for sure, because if the green file.
Yes.
Yeah, never mind.
Right, for example, right, you got it.
Yeah.
For example, if this block maybe stores the content of your root inode,
Yeah.
okay, doesn't get changed, right?
Yeah.
So you cannot rewrite this one.
Oh, that's way less exciting than the thing that I have
I'm not familiar with the system calls, but does the Unix let you modify inode directly bypassing the system call, or can you basically tweak with the
No.
system?
No.
Physical system.
No, it's encapsulation, so that's maintained by the operating system.
Because then you can hide content that's not on the physical.
Then you can make errors, right? You can still see it, for example, as I said, that system call, give you all the metadata information. Those are the metadata information stored in the inode. There's no way, they can even allow you, there's this hex reader on the disk. You can really look at all the pointer values. But there's no system call allow you to debug the pointer. Any other questions? Okay, garbage collection, right? If you don't garbage collect, you can run out of disk space relatively quickly, right? Now, if you are in this research business long enough, you kind of know every paper, there is some part it breaks down. Some part it breaks down. If the authors are honest, they will tell you up front, okay, in the introduction, the limitations, right? Sometimes you have to refer, right? This garbage collection is going to be quite complicated, all right? Let's first look at what the garbage collection conceptually need to do, right? Again, you are basically running out of your disk space, right? And then at some point, right, your disk look like this. They have a bunch of blocks. They call them together as a segment. It's large enough, right? Basically, a large number of blocks is going to be called segment. And then in this segment, right, these yellow ones are in use, and the gray ones are going to be garbage, right? Again, to maintain their performance, they really assume that you have large number of consecutive blocks that are free for them to use, so they can do large sequential write. But this breakdown is fragmented, right? So they want to do garbage collect, they have to compact. They have to read this entire segment, find out what are alive, what are garbage. That's relatively simple for them to do. They have some bitmaps in each segment to tell you which is alive, which is garbage. That's not a big problem. And then they need to compact it so that they write these two in-use block into a new segment in two consecutive blocks, and this entire segment now is free. Back system they can use, right? They can really wrap around, right? Start from the beginning, okay? Doing this, implementing this is not complicated if you do not care about performance, okay? You can do this. Then the question is, how often do you do it? When do you do it, right? Those are the basically practical questions, okay? They don't have a good answer, right? You read the paper. They say we do simulation, right? Because it's not very easy. In principle, you can always come up with a workload model that will say, okay, you are going to really degrade the performance, right? They say, okay, we get a bunch of traces, right, from the real world usage, and we do simulation. We figure out what is the best time and how many seconds that together we should garbage collect, right? At what time, how much disk space we should garbage collect, right? But then later, some Unix developers really try to implement it in Unix. They did implement it, and they found they can never get this garbage collection to work under good performance. Okay, they tried all these policies. They found it doesn't matter how they try. Under any workload, constantly they can have up to 40% performance degradation compared to the fast file system. Okay, so it's just like the problem is the same as garbage collection on any that's managed language runtime such as JVM. Okay, doesn't matter how smart you are. Doesn't matter whether you use Marcus Sweep or reference counting. Swift, Apple use reference counting, right? Still, you get hit. You have this GC pause, right? Time to time again, right? You have it, okay? It's just a hard problem, right? Because you have to be smart enough to know when I need to do garbage collection and how long I do garbage collection. Right? And this garbage collection is even way more slower than the garbage collection for memory, because for memory, it's just memory, right? Your RAM is fast. Your RAM is 1,000 times faster than disk. This garbage collection, you are talking about the I/O, a lot of I/Os, read and write. Okay, so that is where this whole thing really works. Okay. Now it's getting interesting that we are going to get into the impact of this this thing. Okay, so sorry, before we talk about the impact, there's one additional nice feature unrelated with performance. Is that as a side effect, this file system really allow you to kind of checkpoint and rollback almost free, okay? You can almost to say, I want to roll back to any point of my time in the history. Why? Because number one, you don't do in-place update, okay? Your old data is still there, okay? All you need to do is find that old data, right? How do you find that old data? For example, I want to roll back to the, in this example, right? I want to go back to the state before I create this file. The entire file system, right? How do I do that? All I need is to find that inode map. Because remember, your inode map will point into every single file at any given time. What is the latest copy, right? And your inode map is treated as a log. You are not overwriting your inode map. So as long as you can find the inode map at that particular moment, you say, I'm going to use this inode map, and there you go. You don't need to do any additional things. Okay? So, yes.
This is what you have in garbage collection.
Exactly. This assumes you don't do garbage collection. Of course, if you already collected these two things, then that's no longer hold, right? That's no longer true, right? So far, it touches. Okay, now let's talk about the impact. Okay, it's quite interesting, as we said. It's a kind of very new, refreshing idea, and it got some traction. Some people really try to implement it for Unix, but never got it to work. Okay, so for 20 years, the only usage for 10 years, the only usage saw is went into this NetApp, the waffle file system. Okay, so NetApp is an interesting story. So NetApp. So how many of you guys use NetApp?
Sorry, say which one?
NetApp, N-E-T-A-P-P. So if you are using NetApp, is like EMC, right? It's like basically this storage solution provider, right? They sell you a big box, super reliable storage. You can just plug it in, store all your customer database on it. 100% reliable. Always, you can roll back to any point of time, right? Any point of time, you can roll back, right? But you are paying big bucks, right? If you're a NetApp user, you are probably pretty rich, I would say, right? Because they really make a lot of money. The margin is really big.
It starts fast and gets slower and slower.
Yeah. So that's also this, right? Because at the beginning you have a lot of free space, okay? But NetApp is the waffle file system, which is their flagship product, is implemented as log structured, okay? And the reason they actually knew about this was one of the NetApp's early founder was actually Canadian, was a professor in Waterloo, in this community. He read this paper. Okay, that's pretty cool. They founded a company. That's that, right? I mean, and they are pretty good in giving back. Because they really benefited from academia, so they constantly give fundings back to academic professors. So I mean, for example, I got NetApp fundings almost every year, so they're pretty good at that. Okay, okay, back to NetApp. Okay, but this doesn't work. But why NetApp made a lot of money? So basically, they found, okay, what if this whole log structure file system, the advantage is really here, right? But disadvantage is really if you do garbage collection, right? But what if you do not do garbage collection? What if you just have abundant amount of space, right? NetApp customers are what big banks. They charge you really a lot, right? They basically, you're paying a lot of bucks. They give you abundant amount of storage. Storage is cheap anyway, right? They try not to do garbage collection, okay? If you do not do garbage collection, then you have all these benefits. And especially you have this benefit, you can easily go back. Any point of time, you can go back, like instantly, right? Because really, you just need to, again, recover that very small anode map, right? So that is the kind of the impact it made before the advance of SSD, okay? The only system that uses it was the Waffles.
How does it compare with the CFS?
Sorry, I don't know about CFS. Yes?
How does it compare to like Kafka? Like, is Kafka's design essentially?
What is Kafka? Sorry.
Kafka is like it's a
Oh,
only.
okay, so that's not a file system.
No, it's not a file system, but is it not the same?
Sure. Okay.
Idea?
Good point. A lot of this log structured idea, right? Basically, you can only using a lot of cases. For example, recently, do you guys use RockDB? This Facebook open source thing, right? They found MySQL slow. They replaced MySQL with this new database called RockDB. Basically, again, just use log, right? They're append only, so better use of the disk space, right? So this idea is bad, right? As long as you don't do garbage collection. Right? Okay.
But the question, this makes sense when you talk about the physical storage, but all those open source solutions like Kafka, they still live above OS. So how do you create this technology?
No,
It's still OS needs.
Well, it's sort of just blood, like blunders. It's not actually implementing the service.
Well, I don't know what the analogy there,
Yeah.
but in the application level, you can do it. The OS will hide it away from you. You can't say I want to write to block number what. Okay. And even if you do that today, the block vendors, the disk vendors, you think okay that certain blocks have a certain kind of locality characteristic. There's another mapping they will hide it from. Right? They will map it to somewhere in the disk. Right? Later we will talk about it, especially in SSD. Right? Okay. Now we have SSD. Right? Again, this is kind of this. If you look at this solid state drive, the flash is again this disruptive technology when it first came out. Right? It's really small, not comparable to hard drive, and very expensive. Right? But today every laptop you use SSD. Right? Okay, so basics flash. Right? So what is interesting is the hardware characteristic. Okay, so this data is a little bit old, 2013. So the capacity at that time is still not comparable to hard drive, but close. Right? But what really gains this, the latency. Right? Because the way SSD works is completely different. In terms of if you open up, there's no mechanical part. There's basically no mechanical part. So that's why the latency is much smaller. So if you remember that the hard drive latency is milliseconds, this thing to read is kind of 40 microseconds. Okay, this is about 100 times faster than the hard drive. Right? But you notice the write is much slower, still faster than hard drive, but much slower than read. Okay. Later we'll explain why. Okay, and the price is dropping. Right. This is the number I got, the data I got 3 years ago. Today I looked up, it's dropped to this. Right. So again, disruptive. Right. This price is dropping. Right. Price distance to show price is dropping. Right. Okay, but write is really the limitations. Okay. Just because because the hardware, how it works, even if you just want to write for 1 byte, you cannot just write for 1 byte, okay? You have to reprogram the entire page. A page, basically, how large is it is kind of specific to each SSD vendor, but typically at least kilobytes, or kilobytes, even megabytes. You have essentially internally, even if you have just want to write 1 byte, they have to reprogram it. Essentially, they set every bit in this page to 1, and then they flip all the necessary bits to 0. They have to do this, okay? That's the hardware characteristic. So that is why write is slower, okay? Read is fast, write is slow, and also read, there's no locality anymore. Locality doesn't matter, right? It's not a sequential read. It's faster than random read, no, okay? There's no sequential read. Whether you are currently read, let's say, byte number 0, the next doesn't matter is you are reading like the next block or a block far away, doesn't matter. Okay, it doesn't matter. Okay, so because again, there's no this moving part happening, right? Another characteristic of this hardware is that it's burnout. Okay, so you can each cell, each kind of storage cell there, it has a limited lifetime. Right? You cannot write it, program it too many times. Typically, it's up from 1,000 to 100,000. You can only write this amount of time. Otherwise, it's burn out. You cannot use this cell or this page anymore. Okay, that's a hardware characteristic. Okay, so are there questions? Now you should be thinking, what's the implication for the software? How do I design a file system to match this hardware characteristic? Right? Let's take a closer look. Right. So these are characteristics, right? Number one, there's no mechanical components. Data location don't make a difference. There's no difference between random read or sequential read. So basically, all these technology introduced by the fast file system, right, by Bill Joy, gone, useless, right? We don't need it. Okay, you don't need to optimize for locality. Okay.
You don't want to optimize for locality because that means you're banging the same cell.
Exactly. That's exactly right. So later we'll actually see. So random write performance is still bad. Why random write? Okay, let's assume still right now you want to write 2 bytes. Okay, you want to write 2 bytes. You could write them randomly, which means they are far apart. They are not in the same page, or they are in the same page. Okay, if they are not in the same page, once they are in 2 different pages, what do you need to do? You need to reprogram 2 pages, right? Because if you want to write 1 byte, you need to reprogram a large chunk containing that byte, right? So if you want to just, these 2 bytes are in the same page, you just need to reprogram 1 page. Gains your performance and also burn out, right? You avoid reprogram the other page, right? Okay. So which means that all your optimization that try to avoid random writes still valid, still useful. Okay, still useful, right? And also, on every write, a large segment or a page, basically this large chunk of data, I need to be reprogrammed. What does that mean? Remember, what do you need for garbage collection? What is the operation for garbage collection? The reason it's slow is because you need to read the entire segment, right? A big segment. You need to read it, interpret it, and find out what are the live data, and write it back somewhere. Compact it, write it back somewhere. Right? You want to read a bunch of segments, find all the live data, and write it back. Right? This, the hardware is doing it anyway. If you do you are doing in-place update, you just want to write 1 byte, and you are using an old file system, right? You're always writing that byte. Every time you write that byte, essentially the hardware is going to operate on every single bit in that large segment. So that performance is pretty much the same as if you are doing a garbage collection on that segment, right? So basically, I call it basically your garbage collection is essentially free. It's not free because you're paying it anyway, right? Why don't we leverage this to do garbage collection? Right? Yes.
How large are those segments practically speaking? Like what order of magnitude?
I don't know. That's the secret. That's a trade secret. It's kind of heavily guarded by all the vendors, but typical guess is at least kilobytes to megabytes.
I think the paper is
they use, right? But here we're talking about the segment or page, the granularity that you need to reprogram for SSD on every write. Yes.
When you talk about the cells, are the cells like, are there many cells in a page? The cells that burn out when you talk about the
Oh
write?
yeah. Basically that page, right? That page will burn out.
Oh, it's
Yeah. So
so
usually,
a cell
yeah, it's
is
like-
another word for a page.
Yeah.
Okay.
For example, if let's say the page is 4 kilobytes, if there's one bad bit, bad byte, the entire cell will just retire. Okay. And finally, you want to limit it write cycles each cell. How do you design software? You can't really control the number of writes because that depends on the workload. Right? How many times you want to write to a file, it's up to the user, not to the operating system. But what your operating system could do, is you could evenly spread it out. You do not burn one particular byte all the time, where the other bytes left idle, right? The most economic use of this stuff is that you basically spread the write. Doesn't matter what is the write pattern from the user, you want to spread it out evenly across your SSD. Yes.
So why does the OS need to know about it? Because in theory, the hard drive OS is to control basically being the launcher inside. Yes, it's still the same logical algorithm, but it's different cells every time you write.
So your question is why doesn't the OS know about it?
Yeah, why does it need to know?
Good question. If you look at the early days of SSD, you always knows all this. The vendors don't do much, right? The vendors, the technology is not that mature yet. Not too many people are using that, right? They give you a lot of things, okay? They tell you what are the best cells, okay? And you know those, okay? So you always can design certain things around it, okay? But today, if you buy a SSD from Intel, they will tell you if you read the programmer manual, okay? They will specifically say, don't try to change your operating system, your file system. Don't use a log structure file system. Just use your normal FFS, okay? Don't worry about all these these issues. It's not something to worry about from your OS developer. Instead, they do it internally. Again, the log structure file system is in the firmware, okay? Why is that? Number one, it's easier for you to use. You don't have to rewrite an operating system. Number two, they can make money, right? They can make money. The margin, where it's come from, it's not coming from the software. It's coming from, so not coming from the hardware, right? It's coming from the firmware, the software, right? So that is why all these details, such as what's the size of the page, what's the burnout rate, all these things sit heavily guarded secret. Actually, if you read that a little bit, it's quite interesting. They file a lot of patents. There's a lot of patent war. But all these patents, you read it, you never get a big picture. They always just carve out a very specific technology, a patent on it. But they try to purposefully avoid you to know what is a big picture, right? What is their file system look like, right? So that's basically this mix, all right? Okay, then how do you design your software to do this, to address this? You basically just evenly spread it. Use a log structure file system, right? Now if you think about this again, log structure file system is a perfect fit, okay? Number one, you don't care about the read, right? You don't care about like put the two blocks in the same file into next to each other in the kind of in the same track, right? It's not there. Log structure file system is not optimized for read. You don't need to optimize for read for SSD. Read is fast, and there's no difference between random read and sequential read. Okay. Write performance is bad. You want to batch a lot of. You want to avoid small writes, small random writes, but you want to buffer them together and have a one big write. That's exactly a feature offered by log structure file system, right? Garbage collection, right? Garbage collection is expensive, right? But since you need to do it anyway, right? Every time you write, you need to read the entire segment, figure out where the light block is. You just do it, right? I mean, there's no secret sauce, you just do it. But just because if you do not do garbage collection, you use the old file system, essentially performance is similar because you need to reprogram this whole segment anyway, right? Whole page anyway. So you are not losing too much on the performance front, right? And finally, how you want to limit the burnout. Again, log structure file system, don't do in-place update, right? If you have a very hot file, right, you frequently update it all the time, right? Doesn't matter, right? That's that's not reflected, that file is not going to be stored in one particular location. It's going to always moving around, always moved to the end of the log, right? So you evenly spread your write. Okay. That's why log structure process system is a perfect fit. Yes.
So if you got an SSD and every write that you make is a new page that it's an append, so it's a fresh page that you're copying most of the bytes from some other page and changing a few.
Something.
And if that happens every time you make any write, it seems like, my computer is doing lots of small writes all the time, like updating caches and whatever, logs, so it seems like my SSD should be burnt out by now. If it would just be kind of wrapping around and doing garbage collection and.
Good question. Number one, I don't know the answer again because no one knows how Intel and all these SSD vendors they implemented. But a lot of the study suggests that they really cache, they really buffer all your small write together. In your SSD, there definitely some cache. Okay, the firmware, there's some chips that definitely is cache before they write it to the to your actual SSD.
So they just try to, and that minimizes the number of new page updates.
Exactly. Yeah. They are again. They basically implement all these log structure file system, what we discussed, like cache in your SSD. You're paying that when you buy that SSD. Yes.
Can you still append it within a page?
You technically can do that, but the way you do it, you are essentially you need to reprogram the page anyway, right?
Oh, you do need to still.
Yeah. Doesn't matter how many bytes you want to write 1 byte or you want to write the entire page. Every byte in the page got reprogrammed.
But if, let's say you wrote the first 2 bytes and you knew the rest was reprogrammed, could you keep just reading without reprogramming each time?
No. That is why they have to cache it. They do heavy caching. All right. And that's pretty much, that's my last slide, okay. So in the early days, when the Flash first came out, people are doing it in software, right? Like this GFFSS, this is probably widely used as basically part of the Linux. That's a really large structure process, right? But later when SSD is really take on the mainstream, and the vendors are right now doing it in the hardware. So today, your file system is pretty much a similar file system as the old fast file system. But internally, the log structure file system works in your SSD, in the firmware. Okay. So, yeah.
So what happens with hybrid storage arrays and log file system?
Like by hybrid, you mean you have some
Well,
of.
you might have SSD read cache, but mechanical storage right too.
Yeah. Then I guess you have to have different file system on each one, right? Otherwise, you can't. Log structure file system doesn't really work on hard drive, right? Unless you don't care about space, right? You don't do GC, right? But that's an interesting question. I don't know. Today, if you buy a box from NetApp or EMC today, they do have this hybrid. They are selling a hybrid box. I don't know how it works. Okay. All right, and that's again in retrospective, your summary, right? It's a good idea, right? At the time it published, a really refreshing idea. Never really worked until SSD came out, right? None of the motivation they listed in their paper was true, and actually there wasn't even their original motivation, right? As I discussed, they were trying to solve this journaling problem, right? They have this good idea, they package it well, and then reaching the paper, eventually got this use.
I did look at the paper, and my recollection is they claimed they did by basically dividing the 2 files into 2 kinds of files, the ones that get updated really frequently and the files that don't get updated frequently, my recollection is they said they did solve the performance problem. Is that correct?
For all these, they so I don't don't know whether they really kind of have separate policy, but they did do experiment on policy, right? This trace driven, and of course you can. This thing really, the performance really depends on what's your workload characteristic, right? And they were pretty honest that they upfront they say it's driven by workload characteristic, right? But then, you can always find some workload that just works really well. Then again, really kind of it started a big debate in the system community by people who try to implement in Unix, and they found in the real workload it just you will just hit this GC. It's like today you read any this Market Suite GC paper, right? It's all look nice, right? But once you use it, there will always people complaining I have this big GC pause, big GC pause. It's the same.
What happens after NAND flash is gone? We got some newer, better options for SSD. Are they going to harm log file systems again?
Good question. I don't know. There's a lot of research going on about this like PCM, right? A lot of people, it's not even file system. People say you just replace the memory, right?
Yep.
If your RAM right now become persistent, your system, a lot of design decisions may change, right? Personally, I don't know. I also don't. What is going on in the future is also unclear.
If you go non-von Neumann, everything changes. But if you stay with SSD, but just get rid of NAND flash, it's fairly minor change. No, less minor. So less major.
So I don't know. What I'm going to say is BS.
That's not likely to get hidden the same way that the manufacturers are hiding the log file system in their firmware.
Yeah.
If the underlying performance characteristic changes, they're just likely going to say, use it with blocks, use it the same way you
Exactly.
maybe. Whatever changes we need to make, we'll hide them, we'll put them under the
But I think one disruptive thing is that if really they can make whatever the persistent storage as fast as DRAM today, let's say under millisecond, in the bring it to microsecond magnitude, then that really your software will change, because today OS a lot of decisions made by your memory. Number one is way faster than the disk, but on the other hand, it's not persistent, right? You're going to lose things, right? So if your memory is persistent, your disk is as fast as memory, and yet it's persistent. I think definitely there's a lot of opportunities for the software.
I can think of something where the workload of this, like it's sort of a shame that they're hiding the garbage collection of firmware. Because if you had something like a high performance cache and you had like a little bit of RAM and memory map a big file, you don't care if you lose stuff in the cache, right?
Yeah.
So you just loop around and write over and over and over again.
Yeah.
You can't get access to that.
Yeah, exactly. So that's a valid point. A lot of people are complaining that they really want to see, they want to expose more information so they can build better software. My guess is that, for example, if you're Facebook or if you're Google, they probably do some customization for you. Oh, am I recorded? Am I recorded?
Yeah.
Okay. Maybe that Q&A part
Maybe easier question, or at least more pragmatic. What happens to log FS with Hadoop and distributed compute nodes?
Oh, I think it's perfect fit actually, because for this Hadoop, all this workload, you basically you do batch processing. You read a bunch of data, you write a bunch of data. You have this sequential write characteristic, right? But on the other hand, you may write a large amount of data. You do GC, so but I think okay. In other words, maybe on the other hand, I would also think that maybe long structured file system is not that useful because your workload already exhibit this large sequential write pattern anyway, right? You don't have random writes, right? You don't have random reads, just sequential read, sequential write. So your whatever your original file system is just work. But that's an interesting question. That is an interesting question.
let's give a round of applause to